Welcome. In this lecture, we are going to recapitulate our fixed frequency and variable frequency modulation technique. So, in this class, we are going to talk about overview of fixed and variable frequency modulation techniques. Then, we want to summarize various fixed frequency control methods. Then, we will summarize variable frequency control method, and then some ripple parameters, that means the steady state ripple parameters under fixed and variable frequency modulation. We want to summarize like their comparative study, and what are the benefits and shortcomings that we will discuss. So, first we want to recollect that feedback control of a buck converter. This is the diagram, where this diagram represents, this is the power stage, and we have this sensing circuit which will be used for stepping down the output voltage, as well as there is a current sense amplifier. So, but there are various ways of sensing current, and we may not need current feedback all the time, and then we can use various feedback control. So, depending upon the feedback architecture, we have to select the right feedback control, and we may also consider feed forward control, and then finally, the control signal has to be translated into gate signal, and this is where the modulation technique will come. So, in this context, this modulation technique, when you will convert into timing parameter, that means we have to generate a set of on and on off time for this to switch. So, this can be achieved either by using a fixed frequency modulation, where the time period will be fixed, and we will adjust the on time, that is the duty ratio. And this technique is called pulse width modulation, where, and we have learned this thing in the previous course, that pulse width modulation means the time period remain fixed, and we have to adjust the width of the pulse, that is the on time, and by means of feedback control. Then the other control is a phase shift modulation. Although this is not straight away applicable in this converter, but if we take for example full bridge converter, and there are many other converter like a dual active bridge, where the time period is fixed, but in between two bridges we can always consider a phase shift. So, this is another kind of fixed frequency modulation technique. Then pulse skipping modulation, where it is generally considered under light load condition in discontinuous conduction mode, where number of, actually this pulse skipping means there is a charge pulse and skip pulse, and this number of skip pulse will be decided by what is the load condition as well as input voltage. Then if you go for variable frequency control, we have learned in the previous course, that means one is the constant on time control, because if we consider the pulse width modulation, here we keep the time period fixed and we adjust the duty ratio. In this case, we are keeping the on time fixed and we are adjusting the off time by means of feedback control. So, this is the time period will vary depending upon the variation in the parameter or maybe operating condition. The another modulation is the constant off time, where off time is fixed, but the on time will be adjusted based on the feedback control and depending upon varying operating condition. And we have discussed that this constant on time modulation is analogous to leading edge modulation, okay, and particularly when you consider current mode control, and these techniques are gaining popularity because it offers inherent current loop stability, and all these things we have discussed in the earlier course. So, we will actually provide some reference, particularly which techniques will be available in which lecture in the previous NPTEL course, and one can refer for the detail of this mechanism, control mechanism. Then another is the constant off time that we discussed, another is the hysteresis control, where we the on time and off time both varies, and it is decided by the hysteresis band and the feedback signal. I mean how does, if there is any change in load current or input voltage. So, depending upon this variation, the hysteresis control, actually there can be variation in the switching period or the time period. That is why it is under the variable frequency control scheme. So, one thing we should keep in mind, depending upon the various modulation and control, in fact this modulation and control, they are interlinked. That means when I say modulation, fixed frequency modulation, then we talk about voltage mode control, current mode control, trailing edge modulation, peak current mode control, then leading edge modulation, valley current mode control. all this mechanism, there are certain things which you should keep in mind. One is the ripple parameter, that means every converter has to satisfy, or the ripple should be within a certain limit, it should not exceed. Similarly, this ripple also impose a constraint in terms of switching frequency. So, the switching frequency should not vary drastically, particularly when we are operating under continuous conduction mode. Then another important factor is the losses, and when you go to light load condition, then we have to shift to other control, for example constant on time, so that you can save the light load efficiency or you can improve the light load efficiency. Another aspect is the stability, that means which control technique will offer inherently current loop stability or maybe in enhanced closed loop stability, and under digital control, when we will consider one by one their digital version of this modulation technique, we will find that the stability can be affected under different modulation technique while considering the sampling delay. So, why so many modulation technique? That we have discussed that if you go to fixed frequency control, for example, the fixed frequency control, there is always an external clock, and here in this case we call it as a switching clock, and this clock, at the rising edge of this clock, the switch is generally turned on. That means the basic fundamental of this, there are two type of modulation in fixed frequency. One is the trailing edge modulation, and this is exactly the trailing edge. So, one thing that any fixed frequency control, there should be a synchronized clock, that means generally it is an external clock. This clock should have a fixed time period T. But now the question is, how do you synchronize this clock with your switching mechanism? So, under trailing edge pulse width modulation, again it is pulse width modulation, that means we adjust the on time, effectively it actually adjusts the duty ratio because the time period is fixed. Now, in trailing edge modulation, at the rising edge of the switch, that means the external clock, we generally turn on the switch, because the switch is turned on at the rising edge of the clock, and switch turns off based on the feedback condition. That means there will be a comparator depending upon whether it is a voltage mode control or current mode control. So, the feedback comparator output actually changes the state, that means from on state to off state, and once it turned off, it cannot turn on till the next rising edge come of this clock. So, that means this is the latch operation. So, we know about trailing edge modulation, and trailing edge voltage mode control we are already familiar. Then peak current mode control, another example of trailing edge modulation, where we turn on the switch at the rising edge of the switching clock, and the switch turns off when the inductor current hit the peak current limit, and then it turns off. Another trailing edge modulation is the average current mode control, where we generally take the average, that means that we pass the inductor current through a low pass filter, and then the average value is extracted from the low pass filter, and that average is compared with a target or basically a reference current reference, and that error passed through a PI controller, and then that PI controller output is compared with a sawtooth waveform, which is similar to like a trailing edge modulator in a voltage mode control. So, this is also under trailing edge modulation. Leading edge modulation, in the leading edge modulation, generally at the rising of the switch, the external clock, the switch is turned off. That means switch turns off at the rising edge of the switching clock, external clock, which is this clock, and switch turn on based on the comparator condition. It is just the opposite to the trailing edge modulation, and we generally tell leading edge modulation in voltage mode control is generally not used, but this is just for sake of example we are showing. But valley current mode control is a good example of leading edge modulation, where we directly control, that means if we take the inductor current waveform for example, and if we draw the inductor current waveform, that means this is the inductor current waveform, and this should be our current reference, then it turn off like this. So, this is like our reference, and generally this is our switching clock, that means this is our switching clock, and next switching clock means it should be turn off here. So, I like that. So, this is our FSW, and this is my inductor current. So, this is valley current mode control, and voltage mode or current mode also you can have a pulse keeping mode control, and I will show you the reference where you will get the detail. Now, trailing edge voltage mode control, which we have discussed, that there is a control voltage, generally it is the output of the voltage controller, and it is compared with a sawtooth waveform, and this sawtooth waveform is nothing but this red waveform sawtooth, and this control voltage is compared with the sawtooth waveform, and this control voltage is the output of the compensator, which also have a voltage feedback. So, if there is any switching event or any noise, then there will be noisy output at the comparator, and generally after this comparator we put a latch circuit, so that once it turns off it cannot turn on again. So, it will become insensitive to that multiple chattering, that means on off pulse. So, it will be just turn off, and this is the latch operation. That means after this comparator we should use a latch operation. Once it turns off, then it cannot turn on again, and that is called trailing edge modulation. So, the basic concept of trailing edge modulation, the switch will turn on at the rising edge of this clock, and you can see switch is turned on, but the switch will turn off when the comparator actually the ramp sawtooth waveform goes above the comparator, and that will decide the turn off. So, by means of this feedback control, the duty ratio will be adjusted and you can achieve the desired voltage regulation. If you talk about peak current mode control, again the switch will turn on at the rising edge of the clock. You can see switch will turn on and inductor current will start rising during the on time, irrespective of whether it is a buck or boost converter. When the inductor current reaches the peak current, which is the control current or the peak reference, then switch turns off, and once switch turns off, it cannot turn on again. It will again turn on at the rising edge of the clock, and this is under trailing edge modulation. Again we need to use a latch circuit in order to avoid, because if there is a current sensing noise, this will protect multiple switching. So, it will just turn off and it will remain off throughout the rest of the interval. So, the controlling, we are controlling the peak value of the inductor current. Then if we take the leading edge, I have discussed, that means at the rising edge of the switching clock, the switch will be turned off, and when it hit the peak valley current reference, then switch will again turn on, and then again you need to use a latch circuit in this case, because there can be noise in the current sensor, and this valley current mode control. And we have also discussed that peak current mode control, the current loop, inner loop is generally stable if the duty ratio is below 0.5, but under closed loop even slightly lower than 0.5 also the closed loop system can be unstable. But if we just use a constant current reference, so up to 50% or just below 50%, the peak current mode control or the trailing edge modulation, that will be stable. But in valley current mode it is just the opposite. At lower duty ratio less than 50%, it is unstable current loop, and it will be stable when the duty ratio is above 50%. So, that is why leading edge modulations are generally not used when you talk about low duty ratio operation, but it may be used for high duty ratio operation. Now, going to variable frequency control, we know about the constant off time control. This constant off time control, in fact, about the current mode and voltage mode, their relevant reference we have discussed in the previous lecture. That means, in the previous lecture we have discussed where can you get the details of current mode, voltage mode control. Now, we will talk about variable frequency control. Constant off time, which is analogous to trailing edge PWM, and we will see how it works. And this can be either peak current mode control or it can be voltage mode control also. Constant on time is analogous to leading edge modulation. That means, in the leading edge the switch will be turned off at the rising edge of the clock, and we will show why it is analogous, because here under leading edge current mode control it was a valley current mode control, and in constant on time also we will get valley current mode control. Okay, so we can also have valley current mode control, and we can also have voltage based control. Okay, and there can be constant on time pulse frequency modulation, particularly when you consider discontinuous conduction mode. Then we can have hysteresis control, either voltage based or current based, and the current based hysteresis controls are often used. Now, if you go to constant off time, how does it work? You can see there is a peak current reference, and which is coming or which may come from a outer voltage loop. Either you can use a constant current reference or it can be output of a voltage controller. Then how it works? So, initially inductor current rises, and when it hit the peak limit, then switch turns off. When switch turns off, then as the name implies, it is constant off time control. So, it will trigger the monoshot timer. and monoshot timer will be off. I mean, it will turn off the switch for the fixed duration, which is this duration, which is our off time. So, this is the fixed interval when the monoshot timer will be enabled and the switch will be off. Once this counter, the timer is elapsed off time, then the switch will turn on again. So, in this case, we are essentially getting peak current mode control, because once the timer is elapsed, that means here the counting value is over, then switch will turn on, and once the inductor current hit the peak current limit, then the timer is again enabled, or monoshot timer. So, this is similar or analogous to peak current mode control, but here the fundamental principle of timing, generation of timing signal is different. Here we use a variable frequency on timer circuit, that means a monoshot timer, but in fixed frequency we use a switching frequency clock of fixed switching frequency. Here we again compare inductor current, and there is a monoshot timer, and this monoshot timer will turn off the switch. When the monoshot timer is enabled, it will simply turn off the high side switch. We can also have constant off time voltage based control, where the same thing, we can take the output voltage ripple. When the output voltage goes above the reference voltage, then we will turn off for the fixed duration. Again, once it is elapsed, then voltage will start falling, and again it crosses the Vref, then switch will turn on. And this thing we have discussed, and we have discussed in lecture number 21 in our previous NPTEL course. This is the control and tuning method, where we can get the detailed operation of constant off time modulation, and we have also discussed there might be a problem, the system might collapse, then you need to introduce a minimum on time, and that is very common in any commercial product. Under constant off time, we should have a minimum on time. Then if you talk about constant on time, again it is just the complementary of the constant off time. That means when the output voltage goes below the reference voltage, then the monoshot timer is enabled. Once the monoshot timer is enabled, then the switch will be turned on, and the switch will be turned on for the duration which is nothing but the on timer, which you are setting. This is the on time set by the monoshot timer. Once the timer is elapsed, then again the switch will be turned off and the voltage will start falling after some time. And this is the fundamental modulation block, where we will compare the reference voltage directly with the output voltage, then comparator output will go to the monoshot timer, and then monoshot timer will turn on the switch. And here also we saw in lecture number 20 in the previous course that such control can also can suffer from it may collapse, and that is why we need to incorporate a minimum of time. So, all commercial product of constant on time control should generally consider a minimum of time. Okay, this is just to avoid any possibility of voltage collapse, or it is a very common for this constant on time control. Okay, and we have discussed in detail in this lecture. Then current hysteresis control. So, if we sense the inductor current, here I am just showing the actual inductor current, but here you can use a sense inductor current. Then we want to retain this inductor ripple within the band of hysteresis. Okay, and then this control is called hysteresis control, and this is a general representation of a hysteresis control mechanism. But when you go to actual implementation, you may use a single hysteresis comparator rather than two comparator. So, you can use a simple one comparator, hysteresis comparator, but this is just for understanding using two comparator. And again the details are discussed in lecture number 22 in this NPTEL course. So, we are already familiar with this type of. Why I am telling all this? Because before we talk about digital control or digital version of this kind of control, we should first recapitulate the analog version of this. Okay, so, the worst case analysis we have discussed in lecture number 23, that pulse width modulation, the output voltage ripple, that means the current ripple will be worst under highest input voltage, and this is for a buck converter in continuous conduction mode. If you take constant on time, the highest input voltage will also have maximum ripple, the worst case, and in constant off time it will be insensitive to input voltage variation. Also we have discussed the RMS current worst case, and the worst case RMS current is same, you will get the same result as of the ripple current, because we know for a buck converter the RMS current square is nothing but the load current square plus delta L square by 12. So, if the load current is same, the RMS current and the current ripple, if the current ripple increases, then RMS current will also increase. So, generally the worst case inductor current RMS value will be again under highest input voltage condition, and it will also happen at the highest load current. Under constant on time, it is again highest input voltage and highest load current, and under constant of time ripple is insensitive, but the RMS current can be worst under highest load current condition. And we have discussed in lecture number 23 various ripple characteristics, and we saw such variation in the ripple may not be acceptable when there is a switching frequency variation, and this is exactly we are discussing. So, under fixed frequency the switching frequency is fixed. Then under constant on time modulation, the switching frequency will depends on the input voltage and output voltage. So, we need to take special care. In fact, the switching frequency can also be a function of load current if there is a parasitic drop. Okay, although that variation is not significant, but that can happen, and this expression will be different under discontinuous conduction mode. But we generally want under continuous conduction mode to be constant switching frequency. And in this lecture number 23 we have discussed these are the drawback of variable frequency control because of the switching frequency variation. But in this digital control course we want to show, so in general if you want to regulate the switching frequency in analog control, we need to have a separate frequency loop. That means either you adjust the on time slowly in order to regulate the switching frequency, but this on time variation has to be very slow compared to the feedback loop bandwidth. So, it has to be much lower than the bandwidth of the controller, control bandwidth. Similarly, for the constant off time we can adjust the off time, but once we go to digital control I will show you such mechanisms are very simple, because you have a digital counter and you can use a time to digital converter just to lock the frequency, may be very fast in fact, and without additional resource like analog control. So, here we can do it because in digital platform we will have a counter, so we can very effectively adjust the switching frequency. Now, worst case inductor current ripple for boost converter, actually these things are also discussed in lecture number 23. So, I am not spending too much time on this. That means, if you go for current ripple is boost converter, it is the highest at the half of the, when the input voltage becomes half of the output voltage, that means the duty use is 50%. Under constant on time modulation, the current ripple is highest at the input voltage, at the highest input voltage. Under constant off time modulation, the current ripple is highest at the lowest input voltage condition. But all these things also suffer from switching frequency, and fixed frequency control it is fixed. So, in variable frequency we can actually adjust this timing parameter for both the techniques in order to regulate the switching frequency, and we have discussed about comparative study of this control in this lecture. But in this particular lecture we want to recapitulate this modulation technique which we have already discussed, but we want to emphasize that variable frequency control inherently suffer from frequency variation, but this is the starting point of digital control, where I will show you that by means of digital loop or maybe a counter you can very effectively control the switching frequency. But that means the ripple under steady state, if you can match the switching frequency of fixed frequency, that means you can achieve the desired switching frequency, then the ripple parameter will be same worst condition is applicable, because we are slowly adjusting the, and essentially you are getting the time period exactly identical to a fixed frequency control. Okay. But when you talk about stability, because in fixed frequency control we have discussed in lecture number 23 that peak current mode control suffer from current loop stability. That means, if the duty ratio start going slowly, rising above 50% or even slightly less than 50% also, you will have a current loop instability problem, and then we need to add compensating RAM, and that can make the system sluggish. And similarly for the valley current mode control, same problem, at higher duty ratio is stable, lower duty ratio is unstable. So, but if we go for variable frequency like constant on time or constant off time, the current loop is inherently stable. So, when you are talking about the wide duty ratio operation, or we have also discussed that if you are going for a buck converter peak current mode control, generally we will not get sufficient time when the duty ratio is very low for the sense current. So, we may not be able to implement peak current mode control because of at high switching frequency or timing constant, but we cannot go for valley current mode control because there will be stability issue at the low duty ratio. So, where the constant on time is a very popular technique for low duty ratio operation, current mode control for high frequency, but the constant on time suffer from voltage frequency variation, which can be easily anticipated by means of digital control, and that is one of the objective. And the transient performance also will show in this case that you may get, because since there is no ramp compensation requirement, or even we will show in digital control when the gain is increasing, even we want to show in hardware also that fixed frequency control under digital control can be unstable at lower gain, where the variable frequency control can be stable at higher gain, and the type of stability we will also discuss. So, we can show this variable frequency control. If you go for digital, this can offer significant benefit over fixed frequency digital control, and we want to discuss extensively fixed frequency control and variable frequency control architecture with some MATLAB demonstration case study. So, in summary, we have discussed the overview of fixed frequency and variable frequency modulation techniques. Then we have summarized fixed frequency control method, we have summarized variable frequency control method, we have discussed ripple parameters under fixed and variable frequency modulation, and we have discussed benefit and shortcoming in various modulation techniques, but still these are under analog control. And if you go to digital control, various shortcoming in analog control under variable frequency control can be anticipated by means of digital platform, and by that way you can actually come up with a more resource constrained high performance controller for the digital solution. So, here we want to stop here today. Thank you very much.